alpha, and then find the maximum at which angle that function is at maximum. Right? That's the standard problem. So what you and there is of course gravity here, and so the first step which you do in such problems always is to introduce system of coordinates, right? So here's my coordinate y, this is my coordinate x. Right? Now then I have that some velocity here, let's say v, it's the initial velocity of the cannonball. And from knowing angle alpha, I know that the x component of that velocity equals v times cosine alpha. And y component of that velocity equals v times sine alpha. This is initial velocity. And that's not what I need. What I need is the distance. Now, I know that there is no forces acting on the horizontal direction. There is only gravity which acts straight down. And there is no forces in horizontal direction. And so in horizontal directions at time t, the distance, the x as function of t equals just the velocity vx times t, right? That's motion with a constant velocity. Now in vertical direction we have motion with constant acceleration, so y as function of t equals v initial velocity, which is y direction, which is well vy, right? Let's call it vy times t, right? Minus g t squared divided by 2. Right? Now it's minus here because my y is pointing up and my g is pointing down there, and so g is negative. So this is position of the cannonball at any moment of time. At any moment of time, I now know the position of the cannonball. So in particular, but I don't need it for any time, right? I need it right here. So what I know about this point is that at this point, y equals 0. So I can find time which it took the cannonball to come here. That's time. This is a time some capital T. Y of t must be equal to 0. Right? So the y of t. So what I need to do then, well, I know y at any moment of time. This is vy times t minus g capital T squared over 2 must be equal to 0. That's my equation for capital time t. Right? Does that make sense? This equation has obviously two solutions. One solution is capital T equals 0. If you put T equals 0 here, you'll get the answer. All right? And the second solution is capital T equals 2vy divided by g. Right? So both solutions are correct. Right? Because at T equals 0, right here, that y was equal to 0. The height of the cannonball was 0. So that solution makes sense. It exists, but it's not the solution which we want. The solution which we want is this one. Right? It's exactly when the y is again equal to 0. So that's the time. Right? And now in order to find L, what I need to do is that L equals x at time capital T. So all I need to do is take the t and substitute it here, which will be what is it? Yeah. 2 vy, this is 2 vy divided by g and multiplied by vx. Okay. Now I know vy and vx, that's initial velocities. So what I have here is v squared divided by g times 2 sine alpha times cosine alpha. Right? Now the only thing which I can change is alpha. So I need to find that maximum at which alpha this function is at maximum. Well, the easiest way to do that is to remember that this is actually trigonometric formula. And in fact, what is written here is just sine of 2 alpha. now maximum of sine is 1, and sine is 1 when its argument equals 90 degrees. So 2 alpha must be equal 90 degrees. So alpha equals 45 degrees. Right? Or pi over 40. Does that make sense?
Yes.
Yeah.
All right. So that's now the next. There was also a question if the answer what will be the answer for this problem on the moon. On the moon we have different g is different, but you see that function does not depend on g, right? The answer doesn't depend on g. It's always 45. So as long as you have uniform gravitational field, that answer will always be 45 degrees. Okay. Any questions?
So what would happen if there was not a uniform gravitational?
Then you see that non-uniform is not descriptive enough. You need to know then how the gravitational field depends on distance and so forth, right? On position of the particle. And then you need to solve all the equations. In particular, this will not be correct. Please remember that this is a solution of some differential equation. We will talk about it later. This is only works when you have uniform gravitational field, and never in any other case. So this is not some law of physics. This is just a solution of some very simple differential equation, right? For very specific case. When gravitational field is uniform. If it is not uniform, we need to write down the equations of motion, that there will be differential equations. We need to solve them, find the trajectory, and then do the same analysis for that trajectory. Okay? Make sense?
Thanks.
All right, so that was the first problem. Now the second one. The second problem, you have a collision of two particles. One particle. So you have what do you have? You have one particle moving with some initial velocity, let's call it capital V, and the other particle is staying put initially, right? Then they collide with each other. The collision is not central collision, right? So then what happens is that after the collision, one particle is going one direction and the other particle goes some other direction. Right? The particles interact here with some force which was given to you, which I'll skip writing because I don't need it. And the question was after very long time. The only thing which is important about this force is that force is decaying with separation. When particles are separated far enough, the force is very quickly decayed down to zero. So after very long time after the collision, the particles do not interact with each other anymore. Now this is actually not always the case. For example, if it was Coulomb interaction, you cannot neglect the interaction in the final state. That's how it's called. No matter how far they are, the particles they still feel each other just a little bit. Coulomb force is decaying, but it's not decaying fast enough. Now, the force which I gave you here decays very fast. It's exponential decay. It's actually square, exponential over square. It decays really fast. So when the particles are far away from each other, they stop interacting with each other. Right? And we can completely neglect the interaction, and then they just going along some straight lines. Right? And those straight lines are because there is no force, right, between the particles. It means that the velocities of one particle and velocity of the other particle will stay constant, right? Because there is no force acting on it. So the angle between those velocities will stay constant forever. And we can go to very long times after the collision, and it will still be the same, exactly the same angle between the velocities, between the vector of velocity. Okay? So, and that's exactly the angle which you were asked to find. So what's initial and now? That's final state. Initial state. This particle is very, very far away. So from this particle. So they also do not interact with each other. Right? There is no force actor. And they started to interact with each other only when the particles are close to each other, and then they somehow interact, and then they split and they separate.
Okay. Would this also account for like recoil of the first particle?
There's no such thing. There's no recoil. I mean, it's just a simple momentum conservation. Right?
Oh, they wouldn't be bouncing away from each other?
You see that one particle goes this way, the other particle goes this way. That's all, right? Does it describe bouncing?
Well, yes. I guess I was thinking of it like originally like linearly, where the other one, like if they were both were conserving their momentum, one would like either stop and the other one would continue on, or the other one would go the other opposite direction that it was originally traveling.
All right. So the collision is not central. Right? So that will not happen. That only happens if the collision exactly center to center of two particles. That's not the problem which is here. They go in separate ways. Right? But again, don't fool yourself in thinking too complicated things. As I told you before, physics is the simplest possible science. So all of those bouncing, recoil, and so forth, they invented by journalists to describe it to people who don't know physics. You do know physics. You already have taken the classes. So just use what you know there. Right? You have some laws of physics, and they will be satisfied, no matter what. Doesn't matter which words you use to describe it. Okay? So let's do that. Now, there is one trick which is very, very useful and to know. It doesn't always work, and I will talk about it a little bit more just in a few moments. So you know initial state, right? Very, very long time before the collision, and you asked something about the final state. Very, very long after the collision. This is a very typical situation when you have to start with conservation laws, not with equation of motion, not if F equals ma. That might or might not be needed, but in many cases, conservation laws are enough to answer the questions. That's why they were invented to begin with. And not all the questions can be answered from conservation laws. In many cases, you have to go back and solve real equations of motion, which are very complicated equations of motion, by the way, in this case. I don't know the solution. But in this particular case, that's actually enough to write the conservation law. So there are two conservation laws here. First of all, energy is conserved, and second, momentum is conserved. Right? So let's start with energy conservation. In the initial state, when this particle is very, very far away, let's draw it very, very far away. Right? The total energy of the system is kinetic energy m v squared over 2 of this particle. Kinetic energy of this particle, which is 0 in classical mechanics, right? Because it's the input, plus the potential energy. The potential energy comes from the interaction between those two particles. But they are very, very, very far away. Actually, at infinity, you can think about it. At infinity, the potential energy will be 0. We'll call it 0, but I'll talk about it later. So this is the total energy of the system at the beginning. At the end, here, long time after the collision, they're already very, very far away. So they still don't interact with each other, and their potential energy is again 0. So there is only kinetic energy. So let's call velocity here V1, and velocity here is V2. So the kinetic the total energy of the system at the final moment is the sum of the kinetic energy of the two. So it's m v1 squared over 2 plus m v2 squared over 2. Right? Now the conservation of energy demands that the initial energy be equal to final energy. So they must be equal to each other. Okay? Now you see that m over 2 is common everywhere. So let me cancel it out and just write that v squared equals v1 squared plus v2 squared. This is the energy conservation law. Now there is a momentum conservation law. So we start writing initial momentum, long time before the collision. The total momentum of the system is the momentum of the first particle, which is m v vector. Right? This is a vector. The velocity is a vector. Right? That's the total momentum of this particle. The momentum of the second particle is 0 because it's not moving. Initially, right? Now, momentum of this particle at the final state. Now we need to write that the momentum of the first particle, which is m v1 plus the momentum of the second particle, m v2. The momentum conservation law tells you that the initial momentum must be equal to the final momentum. Here it is. Now again, we see that mass is the same everywhere, so we cancel it out. And what we have then is capital V vector. That's a vector, right? Equals V1 vector plus V2 vector. Right? Momentum is a vector. It's not a number. It has direction. That make sense so far?
Yes.
All right.
Yes.
That is our two conservation laws. Now, typically, what you need to do is after that, because it's a vector equation. There are some ways to deal with that, but the standard way to deal with that is to introduce a system of coordinates, split the vectors on the components, and then this equation it's two-dimensional case, right? So that equation will tell you will split into two equations for two components of the momentum, and then you can deal with them as normal equations. But I'm not going to do that because there is a simpler way to deal with it, to solve this. Because the only thing which I actually want to know is the angle between this angle between those two velocities. So let me just take this equation and see what it means. So I have velocity v1. This is vector, right? I have velocity v2. Right? And what is drawn here is the sum of two vectors. The sum of those two vectors must be equal to capital V. Right? What is drawn here is exactly this equation. That make sense?
Yes.
Now, what you notice here, that this is a triangle, right? Do you see it?
Yes.
Triangle, right? Now, for this triangle, we look here, and we see the square of this length equals square of this length plus square of this length, right? This is called Pythagorean theorem, and it demands that this angle be 90 degrees. Right? So now if we continue this angle is also 90 degrees. But this is exactly the angle between two velocities. So this angle is 90 degrees. Okay? That make sense?
Yes.
All right, so first of all, notice that the force which I gave you completely didn't matter. Actually, the only thing which matters about that force is that it's potential force. It's not dissipated. So energy is conserved. That can be seen right from the force, but it's actually said there that it's just the force between two vectors. There is nowhere to dissipate anything here. And so that result, that 90 degrees angle, is actually independent on the force which is in between the particles. It will always be 90 degrees. This is the only result which is compatible with conservation law. And conservation laws must be obeyed no matter what. Right? So that's that extra information which I gave you is completely not needed here. I didn't need to solve any equations. I didn't need to write equations of motion. F equals ma didn't matter, because we know that from F equals ma, energy and momentum conservation follow. They can be derived from F equals ma. But that's enough. The conservation laws are enough to answer this question. Not every question can be answered. For example, I could ask you a different question. See that this is line, right, of initial velocity. And I could ask you, what is this angle between the initial velocity and, say, velocity of the particle now? This question cannot be answered with conservation laws, although conservation laws actually help to answer it. Moreover, it actually depends on the impact parameter. You see that it's not a central collision, right? So that line here, the particle is actually moving parallel to it, somehow like this, right? And that angle, this angle between initial velocity and final velocity, will depend on this impact parameter. Which is sort of obvious, right? Because if the impact parameter is far away, so this particle is just moving over here, it will not, that angle should go to 0. But if it goes closer and closer, it becomes larger and larger. Right? This is called scattering problem. It can be solved. There is basically a general solution of it for any potential energy, for any interaction between the particle, potential interaction between the particles. It's quite complicated. It's given by some horrible integral. And for this particular potential energy, I'm not sure that integral can be taken analytically. And so I never done that, but I know how to do so. So what I'm saying is that this angle between initial velocity and final velocity cannot be answered just from the conservation. You actually need to solve the equations of motion. But for the angle between the velocities, you actually between two final velocities, you actually can use just the conservation law to solve conservation law. So there are a bunch of other questions which cannot be solved with conservation laws. It's any dynamical question, in fact. If I ask about anything, what happens in between here, like how much time it takes for that particle to go from here to here, right, and so forth. The conservation laws will not be enough. You actually will have to solve the equations of motion. So the conservation laws, they don't have all the information, but they do have some information about the system, which actually enough in many cases to actually have a final answer. And moreover, they tell you in this particular solution tells you that that angle does not depend on how the particles interact with each other. So if you play in pool, you know that like with balls and stuff like that. The angle between the after the collision, the angle between the balls will be 90 degrees also. Because they do interact somehow, but you don't care about it. Well, except the balls can actually rotate, spin around it, right? And then there is a spinning, there is some other considerations. So when they spin, they start to lose some energy, and that's not considered here. But otherwise, it would be 90 degrees all the time. Right? Any questions?
So in the problem statement, I guess the part that confused me is it says they're point-like particles, so they don't have any sort of volume, is what I assumed. So they
Yeah.
wouldn't be able to have any sort of angle difference when they collide. It seemed like if they're points, they'll only have one way to collide with each other.
Why? They do interact with each other. Now, think about it. What is it? What is collision?
They're repelling each other.
Right. So there's a force between them. And this is the only thing which matters. The only thing which affects motion is force.
Okay, I think
Right?
I get it.
So they will. It's not. They will collide. The force will be different than like this between like pool balls, right? When they make that sound and stuff like that, it will be different. But who cares? It's 2 point like particle. It's actually simpler this way. It's 2 point like particles, but there is a force between them. So that force will affect the motion, and that's why one of them will go one way, the other will go the other way.
Okay.
Okay.
Yeah, I guess I had a similar problem where I couldn't figure out the diagram for this problem. I had a similar problem with that.
Well, yeah, but think about it. All that f equals ma, and it actually will come in the next problem. F equals ma only valid for a point like particle. It's actually not valid for anything else. You are starting your physics with your mechanics is considering the point like particle, which has a force acting on it. Right?
I'm sorry. So why did you tell us they were point-like then?
Because I didn't want you to consider the rotation, the spinning. The non-point like particle is a lot more complicated. Because they actually can spin if they're not point, like balls in a pool, right? They can spin and then they rub against each other. And how do I know how to get the spinning in the account? That's actually quite a complicated story. It's possible, but it requires additional stuff. So the simplest possible object which you can do any calculation is a point like particle. So what it really means is that that's a very, very, very small particle. So that force which I wrote there, right? It was R1 minus R2 vectors, right? The force is a vector. E minus R1 minus R2 squared, vector squared, divided by L squared, right? So this what this interaction means. Let's imagine that one particle is we hold it, right? And we just move in another particle along some axis. So that force will be quite strong. Well, it's actually zero, right? So when they coincide, it will be zero, then it starts growing, and then it decays exponentially. This is the force, right? As function of separation between two particles. So at maximum of that force at some distance, which is pretty much that distance L. I don't remember. It's probably some coefficient L times some number, which is close to 1. Right? So what it means, the point like particle, is that the size of the particle is much smaller than the cell. If you want for that particular case, otherwise it doesn't. Otherwise the formula doesn't make sense. Because you cannot bring the particles closer than twice of their size, right? But in any case, when the size of the particle is much smaller than L, you can treat it as a point-like particle. And but that point-like particle is all the mechanical laws which you know are about the point-like particle. Think about it in the following way: that they taught you that, and I just used that in the previous problem. The following story. I talk about the cannonball, right? So there is a cannonball, which actually has a size, right? It's a finite size, right? Like, I don't know how big the cannonball can be, right? So I treated it as a point-like particle, which moves from one point to another, but it is not point-like particle. It has sides, right? Now, it is laws of physics are the universal. They can be applied to anything. So let me consider a small piece of that ball here. So that's and in order to describe the motion of the full ball, I used F equals ma. Right? F was and then from there I know that the acceleration of the ball is g going down. Right? That's the solution of that equation. Now, but in reality, it's not the ball which is moving. I can think about the ball which is moving as a collection of many pieces. And I can split that ball any way I want. Right? Each of those pieces also moving. So I need to write that F equals ma for each of those pieces. Right? So for each of those pieces, F equals ma, because that's the laws of physics. But now I actually don't know what force acting on it. Because force which acts on that little piece is not just the gravity, it's also all the forces from outside. If I try to break it apart, that cotton ball, it will resist, right? So there are some forces acting inside. And so for that equation, for that little piece, I will actually have to consider all the forces which is acting on it. Right? It's actually completely miraculous that if I do that, and then I write the equation not for each piece, but knowing the motion of each piece, or equation of motion for each piece, I write what is called effective equation of motion for the center of mass of that Conan ball. That equation of motion will be this one again, but only the gravity force will include, and will be included. And the reason for that is exactly the third Newton's law. Then, if one piece here acting, like let's consider this one piece, this is another piece. If this piece is acting on this one with some force, there is another force which acts on this one from this one, and they're equal to each other in the opposite direction. Remember the third law, Newton's law. So when I sum up all the forces acting on the whole ball, they all will cancel out. And the only force which will not cancel out will be the gravitational force. And that's why I can actually use the Conan ball as if it is a point-like particle. But in reality, it is not. And I need to write this, I need to split it on the almost point-like particles and treat every one of them separately and write equation of motion for each of them. And then I have the full solution. So what I'm saying is that it is that point-like particle is the simplest possible object. That's what you start with. Okay? The rest actually becomes much more complicated. So that collision problem has two point-like particles. Yes, it's small particles which are just collide with each other, but there is a force between them. Right? Any questions? All right. So the third problem about the snake. So what you have there is a table, and there is a snake. And at the first moment, the snake was just lying flat. Then it's starting to pick up its head and become something like this. Right? And what you know is that that head is a snake, right? So it's the head is moving with velocity v. You also know that the total length of the snake, L, and the density of the snake, right? The linear density of the snake, rho. So the total mass of the snake is density times length. That's the total length, total mass of the snake. And because there is gravity, it's everything happens on Earth. So the weight of the snake is g times rho times L. And it's the weight of, it's when the snake is lying flat. That's what our, if you measure its weight, let's say it's not a table, it's how we call it, gauge, things you measure weight with, whatever. Forget the word. So that's what you would measure, right? That's the force which you would measure if it's just lying flat. Now, but what happens if it pulls itself up with a constant velocity? Now, I haven't checked your answers yet. I haven't checked the homework solutions yet, of course. But judging from experience, judging from the previous years, I know how it is going this year, but from the previous years, a lot of students write that because of the velocity is constant, there is no acceleration, right? And so it requires no force. And then this is the total answer, the final answer. As if weight doesn't, as if that force is just the weight of the snake and it's not changing. Right? Does it sound logical? Come on.
Well, that means that there's zero net force, but there's still a force being applied, right?
I don't know what's net force is. I'm asking a very simple question. The force on the table. Let's talk about it.
There's just the force of gravity, and then also because of the force of gravity, it has the normal force being applied to it.
Yeah, that's exactly the way, right?
And then plus I guess the force of the snake moving up.
But again, you said that I gave you some logical arguments. The force equals F equals ma, right? So A is 0 here because velocity is not changing. So it means that additional force equals to 0, and the total force should be just the weight of the snake or gel. So my question is, does it sound logical?
Yes.
All right, but that's the whole trick of the problem. It's actually incorrect. And the problem with that argument is exactly the problem which I pointed out before. F equals ma is valid only for the point-like particle. So please, every time you want to use that law, figure out first what particle you are using it for. It can be done only for a point-like particle. All right, so if you cannot name what is your point-like particle, if you cannot point out like with your finger, what is your point-like particle, you cannot use it. Okay? So in order to use that law, we first need to understand what is a point-like particle here. The snake itself is obviously not a point-like. It has length. Right? So we cannot use this law at all for the whole snake. Instead, we need to find out what we can use it for. And in order to do that, let's see that it's actually incorrect to think that the acceleration is 0 for everything here. Think about this piece of snake. Right? So at some time, when the head is here, right, that piece of snake is staying put. It's not moving. Right? But after some time, the snake will be here. And that little piece will be here. And it will have velocity v. Oh. Right? Does that make sense? So it means that at some point of time, that piece actually did accelerate. But if in order for that piece to accelerate, there must be some force applied which acts up on it. And the only way to supply that force is from the tail. Does that make sense?
Yes.
So you see that when you define for yourself, you always start with thinking about, well, you need to write the system of coordinates and so forth. But every time you try to apply a force, apply a law, you need to be very, very specific what you're applying it to, which object you consider, what is moving, what is the object which you consider, and this law can be applied only to a point like particle, to a very, very small particle. It cannot be applied to the extended object. Okay, that makes sense. All right, so let's do that. Exactly what I draw here, what I have drawn here. So let's imagine that this is. Let's consider some very small time, dt. So at time t, that snake was. Let me redraw that in order to simplify a little bit the drawing. So I had first snake was lying flat, then I had it going like this, right? And so at time t, it was like this, right? This is time t. At time t plus dt, t plus dt, it will be here, right? Like this. So during that time dt, very small time, that piece of snake started to move. Now the length of that piece of snake here is the same. Just like it's out of scale. Here. Is the same of this as this length, right? This length equals to this one. Because the snake cannot be stretched as a constant length, right? So this length we know it's v times dt. It's how much that the head of the snake moved up. So the length of this piece is also v times dt, right? So it's the length of that piece. So the mass of that piece is, we need to take the length and multiply it by the density. So this is the length, this is the mass of my snake, dm. Okay. Sorry, it's a mass of that piece which started to move during time dt. Right? Now, velocity, now let's consider this piece only. It's a very, very small piece, right? So it's a point-like piece. At the initial time, at time t, its velocity was 0. Velocity just of that piece. At time t plus dt, that piece has actually come up here, right? And it's already moving with velocity v. So during time dt, the velocity of that piece changed by v. Right? It was 0 before, it's v after. So it's changed by v during time dt. So its acceleration of that piece is v divided by dt. Change of velocity divided by time. Right? So what I need to do now is to write that the force which is needed to move that little piece up, so to start it moving, right, must be equal to mass times the acceleration. F must be equal to dm times a. So let's plug everything in. What we have is rho v dt, right, times v divided by dt. So we see that velocity cancels out. Velocity doesn't cancel. dt cancels out, and what you have is rho v squared. And this is the only force which is needed. The rest of pieces, right, they're moving with constant velocity indeed. And for the rest of those pieces, the force actually zero. Additional force. I mean, there is weight, of course, but we already counted for it. So for the total, there's a net force which acts on each of those pieces will be zero. And the only additional force which is required to move it is coming from that little piece, which is that force which you need to start moving that snake piece by piece. So the total force which is here, which is let's call it vertical force, or M, right? It's normal force which acts on the table, is the total weight, rho GL, plus that additional force, rho E squared. Okay, that makes sense?
Yeah.
Yeah.
All right. So now let me do the same problem, the very same solution, but much simpler. It actually has a simpler solution. In order to do that, I start with F equals ma. Right? And instead of writing it like that, I will write it like m. And then what is acceleration? Acceleration is the derivative of velocity, right? Time derivative of the velocity. So that's dv and divided by dt. It's written for the point like particle, so the mass is not changing. So I can move it under the derivative and write that this is dmv over dt. Right? That makes sense? But right now I look here, and what I see here is momentum. And what I have then, my second Newton's law reads as that force F equals dp over dt. It's a time derivative of momentum. Now, this equation is actually a lot more general than F equals ma. It can be applied pretty much everywhere, all the time. And moreover, like we will learn that there is some reformulation of mechanics, completely reformulating, like we get rid of all that F equals ma and all that forces and so forth. But that still stays, that time derivative of momentum still plays huge role there. Although there will be no forces in that reformulation. It can be reformulated without force. We'll do that. So let me then take this approach, take this the second Newton's law in this form, and apply it to my and apply it to my snake. So here's my snake. Right? So now let me call that height of the head x. Right? That x x is changing with time, right? It's x is function of time, it's moving up. Now let me write simply this, use this equation. For that equation, I need to know what is the momentum of the snake, right? Now, I will only concern myself right now as a vertical force, because that's the only force which I'm counting, which I'm calculating here. So I need the vertical component of the momentum. The vertical component of the momentum, right, is the velocity. So this piece of snake has no momentum, vertical momentum, no momentum at all. It's not moving. Right. This piece, it has a mass which is rho x, right? Rho times the length, and it's all of that piece is moving with velocity v. So this is its momentum. This is vertical momentum. Let's call it, I don't know, perpendicular, right? The perpendicular of the snake. Now looking at this equation, what I see is that F perpendicular equals d E perpendicular divided by dt, right? I need to take the derivative. So it's d. Now I have my momentum here. It's rho dx over dt. Now I look what I have here. I see that rho is not changing with time. Velocity, v, it's the velocity of the head, is not changing with time. It's moving the way it's moving, right? And with constant velocity. And the only thing which changes with time is x. So what I have here is rho v dx over dt. Dx over dt is how fast that x is changing. But that's exactly my velocity, right? Dx over dt is the velocity of the head. X is the coordinate of the head of the snake, vertical coordinate of the head of the snake. And the dx over dt is the velocity of the head. The velocity of the head is vertical velocity of the head is v. So this is just v, velocity. So what I have here is rho v squared. Okay. So that's this answer. That make sense?
Yes.
You feel that it's much easier, right? Okay. So that's the first point of that problem. And now the second one. We need to compute what force must act on the snake in horizontal direction. Now, think about it. In order to understand that there is a force, right? Again, think about it. That you see that. Okay, well, I write it out, of course. Let me restore the previous. This is my snake at some time, and this is my snake in the next point of time, right? So you see that it's actually shifting this way, right? The snake was here, now it's all here. So something is moving, it's up there. It's to the left. And you see that the whole thing is not only moving up, it's also moving to the side. And the part of snake which is moving to the side which has ever increasing mass. Right? At this point, this part of the snake was moving to the left. At this point of time, this part of the snake was moving to the left. So the mass of moving to the left snake is increasing. So its momentum towards towards your left, right, is increasing all the time because mass is increasing. But if momentum is changing, momentum is increasing. There must be a force. Okay. That makes sense? Do you see here that it's shifted? Well, it's moving. see that it's shift, right? So it's shifted. So it started from here, and at the end it will be here. Well, yes. Well, okay. All right. So how? I mean, can you reformulate it in any other way? The snake doesn't really care about it. It's moving up. Yeah. Right. But from the point of view of snake, it's just pulling itself up, right? Now, I do understand the confusion. Don't take me wrong. And if you tell me how to reformulate it, so it's actually it's more clear. Please do. All right. But I mean, the snake is just raising up, and its velocity up is v. That's what it says in as far as much as I can read it.
I think some of us made the assumption that the snake was like pushing itself upwards. So like as the back would move towards the head, where the head is vertically, the vertical.
Yeah, right. It's somewhat different problems than you have to consider that moving part here also. Right. So that it means that it's not just raising its head. It's actually doing like this, right?
Yeah, and that made the most
Yeah.
sense to me when looking at the problem because we're talking about friction.
But it's a friction here also. It's actually more complicated. Well, let's see. What would the answer will be in the other way? Oh, well, but the answer will be the same, right? Yeah, yeah, but it's the same, right? I'm asking about the coefficient of friction. Should be the same thing. It's there's no really difference. I'm not asking. I'm not talking about difference between static and dynamic friction. There's no such thing. That's actually, I'm not sure. I need to think about it, and I will. When I will be grading, I will take that into account, right? And what you say. And if the indication is that you consider that the snake is moving this way, I will adjust it, right? Does that make sense? But again, if you can reformulate this question somehow for the future generations, please tell me. Again, it's that's the best I could come up to describe this story. If it's confusing, please help me. Okay? But I will take that into account while grading. Right? Well, but it's again, the snake is pushing itself upward, right? Right. So maybe I need to write that it's the snake is pushing itself upward, right? Not moving straight up. Maybe you're right. Okay. Again, I'll go easy on that part. Don't worry about it. I will try to see what whether your solution makes sense in the assumptions which you made. Right? So don't worry about the grades, but let me continue just to describe this story. And what will happen in your story, I'm actually not sure how a snake can do that, and it becomes like not very well defined. If I move it like this, I don't know. I need to think about it, right? But let's do that this way and see what actually happens. So you see that part of the snake is moving this way, right? And again, this length, which is moving during time dt, small period of time, is exactly this length, right? But they're moving on the same time, so it means that velocity of the snake this way is also v, right? Because the snake has the same length. But then we can use exactly the same story as before. So let's now see what is our momentum parallel to the table. The momentum parallel to the table, again, the mass at any point, at any moment of time, any specific moment of time, is the mass of that upraised length, which is rho x, right, times the parallel velocity, but it's v. We already figured it out. Okay. So the parallel force then equals the time derivative of momentum with respect to time of the parallel component. Which is again, this is constant. Derivative of x with respect to time is again velocity. So it's exactly the same rho v squared. Right? So that's so what we have now is the normal force is this one, and the force which is to the left, and the force which is to the left is which is our parallel force is rho v squared. Right? But we also know that force must be smaller or equal to mu n by definition of coefficient of friction. So it means that mu must be larger or equal to f parallel divided by n. We just take that ratio of them, which is rho v squared divided by rho v squared plus rho v L. You can cancel rho here if you want. It will be still the same answer. So what is the final answer? Okay, that makes sense? All right. So let's now compute what was the total work which is done by the snake, mechanical work. The total mechanical work which is done by the snake equals to the total change of energy, mechanical energy of the snake. So at first, the kinetic energy was zero because the snake wasn't moving, and potential energy is zero because we measured potential energy from the table. At the final moment, the snake is staying here, right? And it's moving right before the finite moment. It's moving with velocity v up and with velocity v to the left. So its total velocity of the motion is total v squared, right? Equals v squared plus v squared, right? Pythagorean theorem. And the total kinetic energy then is total mass, rho L, of the snake, times v squared, which is 2v squared, right? Times 2v squared divided by 2. That's the total kinetic energy at the final state. And the total potential energy is your snake is staying here. So its total potential energy is just potential energy of its center of mass. So it's the potential energy of the center of mass is g times the mass, rho L, times the height of the center of mass, L over 2. Right? So that's an initial energy was 0, so that must be the total work which the snake is doing. And it will be rho L E squared plus rho G L squared over. So that's answer. Any questions? Come on. Any questions?
Oh.
No.
All right. Okay, now let's oh boy. Let's see what we can do about calculus. I told you that I'll describe you. I'll sort of teach you calculus in 20 minutes. That's about as much as I have. It's of course not really so. The calculus is as usually as all the knowledge, all the learning is only like 5% of it is knowledge and 95% is skill. And the only way to get a skill is to practice. Right? There is no other way to get any skill whatsoever. Like it's the same as playing guitar. You cannot watch YouTube and that will not be enough to play guitar. You actually have to practice those scales, whatever, chords, patterns, whatever it is, right? So you need to. It's a lot of that is practice, and the more time you spend on practice, the better you play guitar or do calculus. It's the same thing. But nevertheless, there are some ideas behind it, and that's exactly the ideas behind it which I want to describe, and that's how we use it, and that's why it is so powerful. Calculus is extremely powerful thing. A lot of problems which are easily solved with calculus, just like I can solve and you can solve them without even writing anything, and it would be impossible without calculus. Completely impossible. Okay? So that's actually quite. Moreover, it turns out that calculus is very, very natural to language to describe the world. Physical, in physics, of course. World for me is physics. And so it's very natural language. Just think about it. There are very, very many pieces of mathematics. Calculus is not is not the only one. There are very, very different kinds of math languages and so forth. These mathematicians are very creative people. They invent a lot of different things. But in order to describe that world, we use just one piece of mathematics, and it's calculus. Just simply because it turns out to be extremely powerful language to describe physics. It's very, very useful. It's actually much easier to understand physics and what's happening in the world with calculus. It makes things simpler. Right? So I want you to understand that we use and Newton invented calculus not to make you suffer, but to make your life easier. Right? It may be surprising, I know, but nevertheless it is. If you don't trust me, try to solve any kind of problem without calculus. So the idea in calculus is very simple. Let's consider any function. So we have x, y, and we say that we have a function which is y equals some f of x, whatever f is. The only thing which we want to demand from that f is that the function is smooth. Now, there are plenty of definitions. There is very strict definition of what does it mean, mathematical definition, what does it mean to be smooth. Completely neglected, disregarded for now. They're very important, but for what I'm trying to say, what I want to say, that intuition is enough. Smooth is smooth, that's all. And So then that function can be represented as some sort of graph. Okay. So let's consider that graph, and it's a complicated story, right? And it's actually the most complicated mathematical calculations is actually when you deal with already this function, because to invert them and so forth, it's very usually very technically demanding thing. But let's consider that function. Let's just take one piece of it, like this one, and zoom in. Right? Let's just take not zoom which you're using, but take like your camera, your photographic camera, right, and zoom into it with your iPhone. So what you will see is the same graph, right? And now it goes like this. Now let's repeat the same story and zoom it more and more to smaller and smaller and smaller distances. Every time we do that, we will see some sort of a line. And by the way, mathematicians actually prove that it's a line, there is no gaps in it, and so forth. But we know that it will be some sort of a line. But let's look at the evolution of that line. So every time, on every step of that process, you see that the line becomes flatter and flatter, right? Does it make sense?
Yes.
So when I do a couple of gazillion times the same procedure, what we will see is some sort of straight line. Okay? But every straight line is described by just two parameters. It's the position of the initial point, this position, right? And the slope. That's enough. If you know the position of the initial point and the slope, you can continue that line easily, right? That's enough. So there's only two parameters. And now the slope, so what is the slope? If you have change of one, this is my x, right? This is my y. So this change is dx, this change is dy, then the slope here equals dy over dx. Right? Does that make sense?
Yes.
Yep.
So what we've done now, let's come back to where we've been and consider it. So you remember that we have we've done that zooming in a couple of gazillion times, right? So we are somewhere very small area on the graph here, and in that very small area, we know the slope of the line, which is here, which is of course just a tangent. Now after that, like a couple of gazillion times, what does it mean that we've done that zooming? In order to understand that zooming, what we have is that we say that dy over dx equals, well, it's delta y over delta x, right? When those distances are finite. But we need to take that limit of delta x goes to 0. And that's exactly our procedure of zooming in. So we get it smaller and smaller and smaller and smaller and smaller and smaller and smaller way. Okay? That makes sense? So it means that our function at each point is described by just its slope. And by that procedure, we can define the slope of that function at every point. So the story behind it is that in every point, no matter how complicated the function is, if it's smooth, no matter how complicated it is, it's a very small region, in very small interval. And that small means that procedure, right? That any function looks like a straight line. And that's exactly the idea behind the derivative. Right? Because that's a derivative, right? That makes sense? So
Yes.
think about it. That's a very, very simple idea, right?
Hmm.
You draw it and you look at it like very closely, and it's a straight line. That's it. And the only thing which we need to know about straight line is its slope. And that's exactly, and that's it. There's nothing else. But it turns out that simple idea has a lot of consequences, which can be used, and moreover, they actually allow us to formulate everything much simpler, because now instead of dealing with some complicated functions, the only thing which we need to do is to deal with some small intervals where everything is very simple. Right? For example, we can find out what is the change of f. What is this change? Right? All we need to do is if we know the derivative everywhere, right? If we know the derivative, if we know the slope, that every time we change dx by dx, we will know the change of that y, right? So simply by taking the derivative and multiplying by dx. So if we now sum up all those little changes for all the intervals, we will have the total change of the function. Right? So what we did now, we split the whole x, right, on many small intervals, infinitesimally small, in fact, calculated the change of the function on each of those small intervals, and then sum them up, all those little changes. And this is the total change of the y. So we can actually restore the function if we know the slope everywhere. Now, if you do the finite interval, let's say, then you will always, of course, be like make an error. Because if you have final intervals, right, what you will have now is you approximate this function with the straight lines at all points, right? Well, the function is not really straight line. But you approximate it by a bunch of straight lines. But now if you take that limit of each of the interval goes to 0, but the number of intervals, of course, goes to infinity, right? Because the sum of all those intervals must be finite. Then your approximation works better and better and better and better and better. And at the limit, it's exact. Right? So this is the integral. And now in order to use it, for example, how do you use it? Well, let's imagine the following. Let's imagine a simple story, right? We have some object, and it's made of some material. And that material is not uniform. Right? So it means that its density different in different points here. And majority of the materials are like that. The uniform when we say that some object is uniform. Like for example, with the snake, right? I gave you the density, the mass density of the snake, line mass density of the snake, right? And I said that it's just a number, but it is not really, right? The head is a little bit heavier. Well, I don't know where is the butt that is, but anyway, I mean, it's the density will change, right, in different places. So if you take two equal pieces here and in here, right, so they have the same length. On the real snake, they will not have the same mass, right? That makes sense. So in reality, density is almost never uniform. It's an approximation which we use because it makes things simpler. But if you have real situation, well, 2 is the real one. So then let's imagine that we want to compute if we know that rho at each point of that the density of that object at each point of our object, we want to calculate the total mass of the object. How we do that if the density is changing? Well, we first start with what is the density. What does it mean that density is changing? What it means is the following: that we take a small piece here, let me draw it like a small cube, right? That small cube has some volume, let's call it dV. And that cube has also some mass. Let's call it dm. And the average density inside that cube, right, is by definition is total mass of that little cube divided by the total volume of that little cube. Right? So what we need to do is to split our, so what is the density then? It's an average density on this cube. But now let's imagine that we take this expression and actually shrink it down. Again, doing zooming, going in, zooming, right? Inside. So we have smaller and smaller and smaller and smaller and smaller volume. And at the limit, it's sort of, it's almost like a point. It never is, right? It's never zero. The volume is never zero, but it's as small as it can be, and even small. Okay, and then this is what is called density at the point, right? So when I say that density at this point is something, what I mean is that if I take very, very small cube here, and I take its volume, that the mass of that cube will be given by rho times dV. That's the definition of density, which changes in space. But now, in order to calculate the total mass of it, all I need to do is to split it on all that my object on a lot of many small masses, right? I need to compute this for each of those masses. Compute for each of those volumes. I compute its small mass. And then I sum them up. And that will be the total mass of the object. Right? That's what it means. Now there is a theorem in math, in calculus, that it actually, when I take that limit that every little piece goes to zero, right? That the value of the limit does not depend on how exactly I take that limit. So those for example, those volumes do not have to be the same. The only thing which is required is they all go to zero. Okay, and then it's a theorem in math which tells us that the result here does not depend on how I split them and how exactly I take the limit. But it's from physics point of view, it's obvious because when it's a mass, it's the total mass of the object. It must not depend on how we compute it. It's something which we can measure, right? But nevertheless, that's the procedure which allows you. You see that the story is that it allows you to know something global about the whole object. It's total mass. When you know just a local value, rho in every point. Rho is local, right? It can be defined local. And total mass is a global property of the whole object. So you can move, like with calculus, you can move between the global and local properties. And it turns out that it's extremely useful, and that's how we can do things. Like, for example, like using f equals ma for an extended object. We have to do exactly the same. We split the object on little pieces and write the f equals ma for each of those. Right? That's what I did in the homework problem. That make sense?
Mm-hmm.
Yeah.
Those two ideas that every function looks like a straight line when you zoom in close enough. That's the first one, and the second idea is that you can actually sum up infinitely many infinitely small numbers, like when we call it integral, right? So that's two ideas actually give you the whole calculus. The rest of the calculus is just how you use them, right? How you compute those. For example, that integral here, it's a volume integral. it can be quite difficult to compute. In many cases, it can be computed only numerically, but it doesn't really matter. By the way, numerically, you compute integrals exactly by that procedure. You split it on pieces and sum up all the pieces, right? Because computer cannot do anything else. It can only sum up finite number of numbers. So what that's those ideas. That very simple ideas. I mean, really, there's almost like nothing there, but it took humanity quite a long time to figure them out, and it was no one but it took Newton to actually do that, and he invented it exactly for that reason, to describe that kind of like different shapes and different procedures and trying to move from global to local and so forth. And he succeeded to do that. And after that, a lot of problems which were extremely hard to solve. Like, for example, if you know that there was that Archimedes, that law of buoyancy. It's the same guy. He is also very famous by being able to compute the area under parabola. So if you had a parabola, y equals x squared. Well, he didn't know that he didn't use that language to describe it, but that's what he was describing. And he was able to compute this area without calculus. With calculus, this is absolutely trivial problem, right? Because what you do again, as Newton told us, you just split it on little pieces. Each piece has this length is dx, this length is y of x, right? You multiply y of x times dx. This is the area of that little piece here, and you sum them up. And you interested in area from 0 to 1, so from 0 to 1. That's it. And then you take this function, compute it, and you get 1/3. Right? Just simple like that. I mean, it took Archimedes, one of the greatest mathematicians in ancient times. Like, I don't know how many years he was looking, he was trying to solve it. He eventually solved it. But I actually don't know how. I mean, it's an incredibly complicated story about it. Okay, that makes sense?
Mm-hmm.
So that's pretty much all for today. I was going to talk about some physics, but well, let's stop it here because I have only 3 minutes left, and it's probably not enough to describe physics. All right, any questions?
Professor,
Yeah.
could you clarify again how you will grade the homeworks?
Fast.
Sorry.
I'll do it fast.
Okay.
What exactly you want to know?
Oh, just how is distributed across the problems? How the points are.
Okay. So every time on all homeworks, all exams, it's exactly the same. The total homework is 100 points. Every problem has exactly the same weight. Okay?
Okay.
So if it's 3 problems, every point has 33 points. Plus 1, which is I'll give for you nice handwriting. Right? And so forth. So if it's 4 problems, then every problem will be 25 points. So each homework is just 100 points.
Okay, thanks.
And exams will be exactly the same.
I actually had a question for the last part of the snake problem with the potential energy. So I kind of misinterpreted, I suppose, of the I thought that the kinetic energy from the rising of the snake itself would have been enveloped within the potential energy of itself. So I just said the total energy was the potential energy. I assume I'm seeing that incorrectly, but like it's
the snake is still moving, right? It's the last point. The snake is still moving.
yes.
So it has potential and kinetic energy.
I thought
that kinetic energy was not converted into potential. A typical situation, I think. Let me try to understand what the confusion is. Typical situation is when you have starting energy, initial velocity, right? And then it's converted to kinetic energy. Sorry, it has kinetic energy initial. I'm getting tired. It has initial kinetic energy and it's converted to potential energy.
Yeah, or yeah, like a ball going in the
Right,
air or
exactly.
rolling down a hill.
But it's when in this situation, this is only because there is only one force, gravity, which is active. Right? But here it's not. The snake is also pushing itself.
Oh, because
Right.
it's the force, because since it's moving at a constant velocity, it's not that force, but it's that instantaneous moment that it's changing its DL basically.
Yes, yeah, well, not
Okay.
DL, but the upper, the X.
Yeah.
Yes, right. So it's moving, it's applying a force, and that force does some work. Right. In standard, when you just throw a ball up, the only work which is done is gravitational. Right. The only force which acts is gravity, and that work is basically accounted for by converting it to potential energy. Okay? All kinetic energy to potential. Here it's not. I mean, think about it. If I take this, right? If I don't know, if I take some mass in my hand, I don't have much mass in my hand, and I'm trying to move it like this, right? I'm doing the work. I'm doing the work, and it's the initial kinetic energy is 0, and there is some initial potential energy. Now I'm moving it up, right? Let's say at this point of time when I'm crossing this other hand, right? I have kinetic energy and I have potential energy. So at this moment, the total work which I do is kinetic energy plus potential energy. The work equals the change of the total energy.
Okay, and just to make sure I have the terminology incorrect, mechanical energy is referring to just the total energy of the system, not the change of the energy of the system.
No, it's all so mechanical energy. No, it's not so. There is also, except in addition to mechanical energy, there is heat. Right? And when snakes rising up, it actually does a lot more because the muscles are moving, right? And they rub against each other. And there is a plenty of heat which is produced by that. Actually, in fact, the majority of work which is doing is actually going to heat.
Okay.
Right? Because of that. Because organisms are not very efficient. You have to convert some chemicals, right? That's what biology is doing. Convert some chemical into mechanical energy. A lot of energy is lost in this process. It turns into heat. And I didn't want you to consider that because no one knows how to do that anyway. So I was asking only about mechanical energy. It's kinetic and potential energy. That's it.
And just to make sure I got that, so what was exactly like when you're doing the difference of your energy from kinetic and potential?
No, I don't. No. I don't do the difference between kinetic and potential energy. I do the difference between initial energy and final energy. Total energy is kinetic energy plus potential energy. Right? So you have total energy at the beginning, which is kinetic energy plus potential energy at the beginning. And you have kinetic energy plus potential energy at the end. And the difference between those two energies is work.
Yeah. Okay. Gotcha.
Right, any other questions? All right, that's it then. Right. Thank you.
Thank you.